I'm Daniel Rainey. I'm from Tucson, Arizona. I go to the University of Arizona. I'll be entering my senior year in mechanical engineering there. Set to graduate in May 2011. I studied this summer. The title of my project was Structural Transitions of Clathrate Hydrate during Nucleation and Growth. And I'll explain a little bit about that. Alright, so I studied simulation with methane hydrate this summer. And the motivation behind that is the formation and growth is widely not too well understood about hydrates in general, particularly, well, just hydrates in general. So we use computer simulation to try to gain some insight to that. The motivation behind that, hydrates, they have a potential for energy storage. 1 meter cubed of hydrate, if released at standard temperature and pressure, like burned or extracted, will produce 164 meters cubed of gas and then be left with 0.9 meters cubed of water. So that presents a novel form of energy storage. For instance, in cars, you could store hydrogen, potentially.
So the ice battery.
Yeah, it brings me to my first finding of the summer. I found 7 main cages as opposed to the 4 that were previously accepted. So I guess here's the percentages here. This is a pretty dominant one, and it sort of serves as a missing link. It has a coordination number of 22 in between the 20 and 24. Coordination number is just the...
So this is the number of rings of that size?
Right. So 1 square, 10 pentagons, 2 hexagons.
Nice.
And you can, if you look closely...
Square is unusual.
Right. So the square puts a little bit of strain on the hydrogen bonds.
All of the new ones have squares.
Right.
That's neat.
Right.
And are they stable, or when you...
They are. These 7, I found, these are the percentages of their stability to get a relative sense. So mostly 512 is the most thermodynamically stable cage for methane, at least. And then this one, 10.3%, is pretty large. I mean, compared to 512.63, it's the same, and much more than 512.64. And then these 2 down here are a little bit less, but I mean, they were still...
So do I understand there's a methane in all of these?
Right. I didn't display that.
Yeah,
I also found something interesting. It was accepted to be pretty improbable that there would be double occupancy in methane.
Of the largest cage?
It would actually, in most cases, just form a completely different cage, like an expanded cage. This is a 512.65. So I guess I could talk about sort of the pride and joy of the summer, about what I found and what I observed are cage transitions. So oftentimes I would have a 512 cage, for example, and there'd be 2 water molecules that would break 2 of the bonds and insert themselves and form the next highest coordination number. So I found that it would go forward and backwards between every one of the cages. I found specific examples.
So it requires 2 water molecules at roughly the same time?
Roughly the same time, right. For it to be clean. I mean, there were times where a cage would just dissolve and then form, but that's sort of a different story. So yes, the cage transition, sometimes these water molecules would come from solution or leave and go into solution, and sometimes, probably about half and half, I would find that they would come from another cage, so they'd come from a solid, and I call that a solid-solid transition.
And would they break the other cage? Or?
They would break the other cage, and I have some videos that I could show you. But so it's been known experimentally. There's different types of structures and arrangements of cages: structure 1, structure 2, structure H, and it's been known that structure 2 will transform into structure 1, and vice versa. And so we don't really know how or why that happens. And these cage transitions can likely explain, if so many 512.62 cages give up 2 and give it to their partner, then maybe cage transitions will describe why structure 2 transforms into structure 1.